Good morning and welcome to the SPE Distinguished Lecturer Series. My name is Phil Ray from BJ Services, and I'm going to be talking to you today on a subject that's not traditional in the oil field community, I guess. It's eliminating environmental risks in well construction and workover. Just to give you an overview of the presentation today, I'm going to start by talking about the oil industry in general and some public concerns and misconceptions about our industry. I'm going to talk about oil and the pollution risk posed by oil and try and put it in some perspective. And then I'm going to go on to the main part of the presentation, which deals with well service chemicals, talk about some barriers to further progress, and I'll round up with some closing remarks. So let's put the oil industry in perspective. Is it an engine of global growth? I would certainly say so, and I'm sure most of the people listening would say so too. It certainly provides us with power, with all our transportation, with lots of raw materials for industry, and of course it's a source of countless dyes, pharmaceuticals, plastics, detergents, lubricants. At the end of the day, it's translated into better living standards for many, many people around the globe. And just a few of the sometimes trivial but sometimes extremely important things that oil produces, seen there. Of course, my flag carrier, Singapore Airlines there. But let's talk about the public perception of oil. There is a big perception out there that oil companies are unscrupulous multinationals, that we as an industry show little regard for nature, and that the oil industry is dirtier somehow than other industries. And of course, there's a very common misconception that practical alternatives to oil exist. This is the kind of stuff that we are all familiar with, the petrochemical industry, which of course is downstream from our own industry, but plenty of nasty pictures of industrial pollution. If we go back to our side of the business, on the upstream side, these are the kinds of things that you may see in newspapers. And unfortunately, it doesn't present a very good picture of our industry. But let's be serious. If you take a look at world energy consumption, then oil is going to be with us for a very long time. In fact, oil is going to increase in consumption over the next 25 years by some 50%. Natural gas also is going to increase, but you can see out of the overall proportion of the fuels that we're going to be using 20 years from now, the vast majority comes from hydrocarbon sources. You may look down at the bottom of that graph and see renewables and think, well, that's good, we're moving towards renewables, and think of wind and solar energy. But in actual fact, the vast bulk of those renewables is hydroelectric and biomass. And in fact, the other fuels, the solar and so on, represent less than 1% of that total production. So oil is going to be around for a long time. Now let's talk about the pollution issues related to the oil industry. There are many. Obviously, habitat disturbance and disruption is something that sees quite a bit of press attention. All the paraphernalia associated with our business of oil exploration. Then is the decommissioning of facilities. And in the last slide there, you may have seen a picture of the Brent Spar, a famous structure in the North Sea that an oil company wanted to take out and dump in the Atlantic Ocean. At the end of the day, they were unable to do that due to extensive pressure from NGOs and the public. The speciality and toxic chemicals that we do use in our business, of course, are something that we're going to talk about in this presentation. It wouldn't be right either to talk about pollution issues if we didn't talk about greenhouse gases. About 26 billion tons a year of carbon dioxide from our consumption of hydrocarbon fuels, and clearly that's an issue that's gaining a lot of press attention. Finally, there's oil itself, and that's really where we start to look at pollution. It is perceived as a major pollution threat. Vast quantities of oil are produced and transported. Currently, the world is consuming about 84 million barrels of oil a day. So obviously, the majority of the markets for that oil are far removed from the production areas, and it has to be transported. When there is a problem, for example, a spill, there's intense media coverage of that spill. And those spills, because of the prodigious quantities that are required every day to feed our world, those spills tend to be substantial. There are numerous infamous tanker disasters, and I have a map here showing some of them scattered around the globe. You may notice up on the far left-hand side the Exxon Valdez, a rather infamous accident. But there are many, and the kinds of pictures that you may see from tanker disasters, of course, are fairly common. Not very pretty. Then there was the case of the retreating Iraqi forces in the first Gulf War, releasing a lot of hydrocarbon into the environment, deliberately destroying wellhead pressure control equipment, releasing actually a total of about 11 million barrels of oil into the Arabian Gulf, and a total of 150 million barrels of oil completely from the destroyed wells. And of course the consequences are, again, fairly well described in the press. These are the kind of pictures we're used to seeing. But there are some facts that we need to consider. Oil is a natural product. It routinely seeps to surface in many, many places. In fact, many oil-producing areas were first discovered as a result of natural seeps to surface. Of the approximately 1.3 million tons of oil a year that enter the oceans, 600,000 tons are from natural seeps. In actual fact, we could even claim to help this situation by relieving the pressure from downhole reservoirs and reducing the seep rate into the oceans. So about 45% of the oil that enters the oceans comes from natural seeps. If you look at the total input from our industry, that's the E&P industry, into the oceans, it constitutes about 38,000 tons per annum, about 3% of the total input into the ocean. So trivial in comparison with natural processes. Now, oil is a rich nutrient source, but it is hydrophobic. It repels water. And major spills tend to overwhelm the ecosystem for a short period of time. But it does quickly degrade if properly dispersed. In the Brer tanker disaster in 1993, a ship carrying Norwegian crude to Quebec, to a refinery in Quebec, was caught in hurricane forces off of the north coast of Scotland. She went aground, and most of her 85,000-ton cargo leaked out into the sea. Unfortunately, they couldn't do anything for days because of the extreme weather. They couldn't get near the wreck. 3 weeks later, most of that oil had vanished. They could hardly find any traces of it whatsoever, proving the enormous power of the wind and waves and the ability to disperse and disrupt the oil slick. But that's no reason for us to be complacent. There's always going to be a risk of escape, and we need to be very careful when we work in this business. The technical frontiers do continue to advance. We're drilling more slim holes with much less margin for error. And we're doing extreme deep water drilling. Some of those reservoirs that we're drilling into are capable of producing at truly prodigious rates. Wells that are potentially capable of producing at 100,000 barrels per day. So if we lose control of one of those wells, we have a lot of oil to deal with. And then, of course, there is, as we're only too familiar, the ever-present risk today of terrorism and sabotage. That's trying to put the oil industry a little bit in perspective from a pollution perspective. I'd like to move on now into the arena of the well service chemicals and the second part of the presentation. There are about 2,500 oil field chemicals in use. It's a little bit of an exaggeration. In fact, there are 2,500 proprietary blends of oil field chemicals in use. There are probably about 1,000 individual chemicals in use in our business. And these materials have a wide spectrum of toxicity and biodegradability. The main categories that we are going to deal with today are the drilling chemicals, the mud and cementing materials, completion and well cleanup and workover materials, and stimulation materials for acidizing and fracturing. Now, it wouldn't be right talking about chemicals without, first of all, describing some of the potential environmental risks from these materials and defining those terms. There are several different types of toxicity, and we need to define them, so let's start out with acute primary toxicity. This is the kind that you would encounter from things like arsenic and cyanide, the classical poisons that you take a spoonful and you drop down dead. But not all materials act in this way. Some of them have much more insidious and much more persistent effects. Clearly, if we put organic materials into the biosphere, there is an oxygen demand in order for these materials to be degraded. Then there's the biodegradation issues. Are these materials broken down by organisms in the environment? Are they broken down under aerobic conditions, where there's oxygen available, or anaerobic conditions? These are important issues because these two types of conditions can coexist. In the open ocean, materials may degrade perfectly well aerobically. That's under oxygen availability. However, if they're buried under a cuttings pile underneath a platform, they may never see oxygen, and they may never degrade. So these are, as I say, important issues. There is also the potential, and we all know something about this, I'm sure, and most people have heard of Rachel Carson and her book Silent Spring in the 1960s. This was a clarion call for environmentalists everywhere when she described the effect of mainly insecticides and so on birds and other animals. There is this risk that materials, fat-soluble materials, will bioaccumulate. They gradually build up in our bodies. Now, today, there are 300 chemicals that are detectable in human tissues that weren't even around 50 years ago. So these materials have only started accumulating in our bodies over the last 50 years, but they're there. And fortunately, of course, most of them do us no harm, apparently. But clearly, there's a risk that some of these materials could accumulate to levels where they can potentially damage us. And that brings me to the subject of so-called false messengers. What are false messengers? Well, they're also called endocrine disruptors. They're a diverse group of chemicals, and unfortunately, they mimic natural signaling molecules. I'm talking about the kinds of things like hormones that control our bodies and manipulate our bodies, if you like, in the everyday process of living. Unfortunately, some of these synthetic molecules that are out there, let's say, mimic these natural signaling molecules a little bit like a lock and key. The lock is our cellular processes, if you like. The key is the molecule that fits into a specific docking site. This specific docking site then goes on to activate all kinds of cellular processes. These materials are excruciatingly powerful. Our own cellular systems are very, very sensitive, and these materials can trigger biological changes at very, very low concentrations. As a result, they've been implicated in things like cancer and genetic mutations. There are several of these materials around in our industry, and I mentioned a few of them. The so-called NPEs, non-alphenol ethoxylates, never mind the terminology, polycyclic aromatics, and phthalates. These are three very, very well-known groups of chemicals, which unfortunately mimic the female sex hormone estrogen. Now, this is rather significant. These are typical endocrine disruptors there, and on the far right-hand side at the top, you'll see para-nonylphenol. This is the base material for a vast number of non-ionic surfactants. Now, these non-alphenol ethoxylates have been banned from our industry for quite some time now in those areas where there is an active environmental protection program. We no longer use non-alphenols. But although we've cleaned up our industry, it's worth pointing out that these materials are still in widespread use for many, many things. In the United States alone, we manufacture 200,000 tons of non-alphenol per year. So other people are using this material despite the fact that the oil industry is no longer using it. Now, what do these things do? As you can see, they're a diverse group of materials, but it so happens that in three-dimensional space, these molecules all look similar to this famous female sex hormone estrogen. So they can mimic the effects of it. They fit into the lock, and they activate the mechanism in the lock, and they do certain things in our bodies. I don't want to go into a biology lesson here, but this is the basic mechanism of action, where you have this material docking with a receptor, affecting DNA transcription and so on, and eventually producing proteins. This is how the system works. Who are the possible victims of this? Well, there's many possible victims, unfortunately. I put a few up here. You may not notice, but the frog on the right-hand side there actually has 3 legs. So this is a victim of these materials in the biosphere. Down on the bottom left-hand side, are human sperm cells. Now, there's a wide-ranging debate about the quality of male sperm in the human population, particularly in the industrialized world, and the falling sperm counts. And this may well, in fact, be as a result of the presence of these molecules that we're talking about in our environment. We're being exposed to them on an everyday basis. Up on the left-hand side is clearly a woman, beautiful woman. And what difference does it make to her? Well, from about 1940 on the left-hand side to the year 2000, that's the span of the graph basically, 1940 to 2000, the graph plots the mortality from breast cancer per 100,000. This is a quite significant increase in female breast cancer rates, from about 15 up to 35 across that span of 60 years. Now, clearly, there are many things that have happened in those 60 years. Many more women are in the workplace. We have much higher marital breakup rates. There's a number of different stress factors that could contribute to these effects. But nevertheless, this is also a period when we've undergone quite extensive industrialization. And this may or may not be implicated in the problem. Let's go on to these main categories that we discussed at the beginning. I'm going to start off with drilling mud, the single biggest well site consumable. There are three main generic types of drilling mud: oil-based, synthetic oil-based, and water-based muds. And it's worth taking a look at the evolution of mud. Originally, mud was water-based. Very simple material. You just mixed up bentonite and water, basically, and drilled. But, of course, problems using this type of formulation, drilling reactive formations. And there was a gradual move through the 70s and 80s towards oil-based muds and invert oil emulsion muds. Why? Because of very good lubricity and the fact they're unreactive with many formations. Now, until about 10 years ago, oil-based muds used diesel oil as the base fluid. But we mainly switched to paraffin oils, which have low aromatic content, to avoid some of the toxicity associated with diesel. Unfortunately, you still just can't dump this stuff. The drill cuttings need special handling. The drill cuttings, of course, are covered in a coating of this oil-based mud. So either you subject them to solvent extraction or incineration, or somehow you land farm them, or you do what a lot of people are doing today: you re-inject them. So you actually stick them back under the ground below any subsurface aquifers, and that's certainly a process that's growing in popularity. But many places use synthetic oil-based muds as well. Now, these are based on vegetable oils, either esters or ethers or alpha olefins. They are biodegradable, and so that makes them a little bit better, let's say, but they are expensive. And unfortunately, or fortunately perhaps, zero discharge rules are being enforced in many parts of the world today. So you can't just put these materials over the side either. You have to do things with them. So there's a gradual move back towards water-based mud, which is more sophisticated these days. We have chemicals to deal with many of the previous drilling problems that made water-based mud unattractive. And the benefit, of course, of water-based mud is it's a lot cheaper generally than oil, particularly today. What about the weighting agent that's in mud? You know, we're drilling into higher and higher pressure intervals. Obviously, we need weighting agents to maintain hydrostatic well control. Barite, of course, is the traditional primary weighting agent that's used in our business. About 6 million tons per annum of barite. Basically, the oil industry consumes about 97% of the world's production of barite. So clearly, we're a major user. Now, unfortunately, this material does contain significant levels of heavy metals, and I'm talking here cadmium, lead, arsenic, and so on. I say significant levels. We're talking in the parts per billion range, but nevertheless, if you're putting in several million tons per annum into the sea, then clearly there's an issue there. Material is often discharged and dumped. So I asked the question, is there an alternative? Well, a few years ago, the Norwegians came out with a paper discussing an old material, an old traditional material, ilmenite, and its brother hematite, if you like. These are oxides of iron or iron and titanium. They've got much lower levels of heavy metal. They're significantly denser than barite, so you need less volume of them for any given mud weight. That results in a lower solid volume fraction in the mud, and therefore much better mud rheology. What does that translate into? Improved drilling hydraulics, less environmental impact. So in general, why do we as an industry not move towards something like this? Something that certainly should be considered. Now, I want to put things a little bit in perspective again here and put my reality check cap on. There are many other sources of pollution. You may or may not recognize this as a so-called smoker. These are the vents that occur near the edges of the crustal plates, and as a result of plate tectonics, the ocean spreading and so on, ocean floor spreading, we get this kind of hydrothermal activity at these vents. Now, each one of these vents is capable of pouring out about 250 tons a year of heavy metals. These are mainly polymetallic sulfides. Some of the deposits around these vents are extremely large. We're talking 100 million tons of heavy metal deposits. These are future ore bodies, in fact, that will turn up over the course of geological time. But this has been going on for the 4 billion years the planet's been around. So, in comparison with the amount of material we put in the ocean, this is a pretty significant contributor to pollution. And you can see that there are many, many of these active sites around the world at the edges of the crustal plates. Moving on from that into cementing chemicals. Well, the good news is cement and cementing chemicals are quite benign, which is just as well. Cement is the biggest commodity product in the world. It really is an enormous business. We're talking 2 billion tons of cement made per year. That's twice as much as there is steel made. And so clearly, everything around us in this world, we basically rely on cement and concrete for so many things. It's clearly quite a benign material. And most of the additives that we use for well cementing are naturally derived products, derivatized celluloses, sugars, lignins. Most of these materials are quite benign. There are a few things which are or weren't so benign. I'm talking spacers and washers for mud removal, which historically used things like NPEs that we've mentioned already, the phenol ethoxylates, and some other materials like the aromatic sulfonates. Largely, these materials, these washer materials, have been replaced by much more bio-friendly materials, alcohol ethoxylates and so on. I also mentioned there an interesting concept, the idea of mixing up the cement ahead of the cement job and taking it to location as a pre-mixed slurry, and that's something that we are capable of doing these days to even minimize the issues of dust and other pollution at site. There's been some technology developments as well in the drilling business. We're doing more slim hole drilling, I mentioned that earlier on. That means less mud, less cuttings, less cement. Typically about 60% less of those materials per well if we go to slim hole versus conventional well architecture. Multilateral drilling, basically one mother bore and a bunch of daughter bores off of the mother bore. That results in fewer wells and obviously improved recovery, which is good news. Underbalanced drilling, less mud or potentially even no mud, and obviously less damage, potentially better productivity. Horizontal and extended reach drilling. Again, this is a technology really in the last 20 years has taken off. Less obtrusive, better contact with the reservoir, better productivity. And this is a very famous project, Witch Farm in the south of England, which is in an area of outstanding natural beauty, believe it or not. That's Poole Harbour there. And you may, in the middle of the picture, see the rig. Drilling 10-kilometer wells out under Poole Bay and tapping reservoir that's, as I say, 10 kilometers away from them. Quite incredible. They wouldn't have been able to do that. Certainly you would not have been able to take an offshore platform and build it in Poole Harbour, I can assure you that. But anyway, they were able to do this. This is a BP development, and they've done that very successfully. Moving on from the drilling process to well completion and cleanup, there are many agents that can impair production that we have to address in the process of the completion or cleanup or workover, and I've mentioned a few of them. I'm not going to read them. Historically, the chemicals that we dealt with those materials with are, as you can see listed there, all kinds of interesting materials. Flocculants like the quartz to get rid of clays. Polymers there, I mentioned the oxidizing agents. Rust and scale mineral acids like hydrochloric acid. Organic deposits, aromatics like xylene and toluene, and so on through the list there. You can see quite a cornucopia of materials, most of them pretty nasty. Well, nowadays we're using a lot less of those materials, a lot more of these materials. So we're using things like polyaluminium chloride as a flocculant, natural enzymes, which are completely biodegradable to destroy and degrade polymers. Neutral derusters to dissolve rust, so we don't need corrosion inhibitors. For some of these organic deposits, we use terpenes, which are plant hydrocarbons based on things like orange oil, believe it or not. These are very, very good solvents, and they are, of course, biodegradable. And, as I say, I mentioned several of the other materials there. I'm not going to talk individually to each one, but you can see clearly we're using a lot of biodegradable materials these days. Now, I'm going to just pause for a second there and produce a couple of articles of faith. I believe that the most effective method for the oil industry to be environmentally friendly is to actually drill less wells and to maximize the productive potential from each and every well. And I would comment that adding production by stimulation is much cheaper than drilling a new well, which conveniently brings me into stimulation chemicals. Now, there are some serious potential bad guys in the stimulation brigade, and they're all listed there, acids and corrosion inhibitors and so on. Talk first of all about acids. Acids actually represent an acute spill problem. They are quickly neutralized or absorbed in the biosphere by buffering capacity of the biosphere. But what is much more problematic are the corrosion inhibitors that are incorporated in the acids. And of course, then when we take returns back, some of those corrosion inhibitors also come back with the acid and therefore pose a disposal problem. Why do we need corrosion inhibitors? We need them because mineral acids are very, very aggressive. I'm talking HCl and HF. And we need to protect our well tubulars to maintain well integrity. At the same time, we need to protect the formation, because if we don't use corrosion inhibitors, we're going to dissolve a bunch of iron off the pipe. That iron is going to end up in the formation and is going to damage the formation. So we need to use these materials if we use aggressive acids. Well, quite a few developments. First is that we've got greener corrosion inhibitors. We've removed a lot of the polyaromatic hydrocarbons, the NPs and so on, that were part and parcel of these corrosion inhibitors. So we've got a lot greener in that sense. But some other things we've done is we've moved a lot more towards organic acids in place of hydrochloric acid, things like acetic and formic, which are biodegradable. We're also using high pH HF systems now, which are 1,000 to 10,000 times less acidic than mud acid, conventional HCl HF. So therefore you need less corrosion inhibitor. Again, that's got to be good news. A technology that's at least 15 years old now, but that is occasionally resurrected, is the idea of in situ acid generation. Basically, you mix an enzyme and an ester, you pump them downhole, you don't have any acid on the surface, so you don't need any corrosion inhibitor, and the acid is generated in the formation as a result of hydrolysis and time and temperature. Other developments include things like process-controlled acidizing, where we prepare acid on the fly. We don't have any waste, no disposal, and it's much more safe and much more cost-effective. We don't have lots of tanks of acid out there on the rig site. Some people have even moved to the complete elimination of acid using chelate-based systems based on EDTA or its analogs, and these are capable of dissolving many oil field scales and so on in the same way that acid can. Potentially also we can move away from acidizing and do some small-scale fracturing, and skin bypass fracturing is one example of that, which brings me conveniently into fracturing technology. We've done a lot here, in fact, in fracturing technology. Instant fracturing fluids, the elimination of toxic metallic cross-linkers, the ability to prepare fracturing fluids on the fly, on location, without having to mix up lots and lots of frac tanks and use lots of biocides and so on. The use of biodegradable surfactant frac gels, and the use of lightweight buoyant proppants. These are interesting materials because potentially we don't need the frac fluid for transporting the proppant anymore. We may not need any breakers, therefore. No biocides. At the limit, no fracturing fluid at all, right? Better cleanup, better productivity. Clearly, that's a little bit of a leap of faith, but that's the way the industry is moving, which is interesting. Okay, so let's take a stock check of where we stand today with green technology as far as well construction, workover, and simulation concerned. About 60 to 65% of the chemicals we use today are, in fact, okay. But it's relatively simple to raise this figure to 90%. The technology to achieve this already exists, and all that's required actually is some commitment and vision on behalf of the industry. If you take a look around the world, the Scandinavian bloc countries in Norway, Denmark, and Holland lead the field in terms of environmental compliance. The UK is actually dragging its heels a little bit, but it is semi-compliant. The US is behind the curve, but starting to make some definite progress in recent years, certainly over the last 10 years. Surprisingly enough, in the developing world, we're starting to see them leapfrog over the rest of us. They're actually applying North Sea rules in some of the developing world, and that's ahead of many other so-called developed countries, let's say. So these countries are actually starting to apply the rules that have been set up in the North Sea, which are amongst the toughest environmental rules in the world. But there are some barriers to progress. How do we move ahead with this environmental compliance issue? Interestingly enough, one of the biggest barriers to progress are the regulatory authorities themselves. It would always be nice if we could revolutionize these technologies, but we can't do that. Sometimes we have to make incremental changes, incremental improvements in these technologies and the use of chemicals and so on. The regulatory authorities would rather have us make quantum leaps. Well, we can't do that necessarily. So they have to allow us to make these incremental improvements. And this is difficult today under the current legislation. Another point I'd make is that there is no harmonized environmental legislation around the world. We have different test species that we test the toxicity on, different acceptance criteria. Some places we have to test complex mixtures of materials. In other cases, we have to test the individual components. And then there are issues of ownership and security of proprietary data. I mean, clearly this is a commercial business, and companies don't like to provide the formulations of their specialty chemicals to government departments. There's also a poor understanding by many people in the regulatory authorities of the actual end use of the materials that we're trying to get certified. I'll give you a few examples of that here. I just happen to put up. This is what I call irrational bureaucracy, the mandatory testing of harmless chemicals. Now, you have to understand that these chemicals all have to be tested for several different things, for toxicity, as I mentioned, biodegradation, bioaccumulation. And these are some of the materials that we've had to test over the years. It's very expensive to do this testing, by the way. Potassium iodide, which is a corrosion inhibitor aid. Potassium iodide is actually extracted from the sea. It's actually used to be extracted from seaweed, but that's where it comes from. It comes from the sea. It's a normal constituent in the sea, and yet to try and put it back into the North Sea, the Norwegian government had us retest it for toxicity. Galactomanase, which is an enzyme that's used for breaking down fracturing gels, this is a material that's actually also used in the coffee industry to improve the filtration rate of freeze-dried coffee, but guess what? We had to test it. A polysaccharide gelling agent, this is a suspending agent that's widely used in the industry. This material is made from seaweed. And again, we had to test it for toxicity before we could use it and put it back potentially into the sea. So this is the kind of stuff that is actually a problem, certainly for us in the service sector, testing materials, which is rather expensive. Now, that brings me on to this issue, cost. Who pays for the development? Well, here in America, there's a great expression, which is there ain't no such thing as a free lunch, and there's nothing truer than that. Ultimately, the operating company and I guess the public pays for the development, but it's difficult at the moment to see how we get recompensed in the service sector. The legislation is a constantly moving target. And in fact, what's good today is not necessarily good tomorrow in terms of testing and in terms of all the certification that you get. Now, I have to say that there is a lack of genuine E&P support, and that's where most of the operators in the room walk out, but there is a lack of genuine E&P support. The supplier is disadvantaged in commercial bids. And I believe that the E&P companies need to send a strong message. They should reconsider bid evaluation criteria and should factor in the cost benefits of waste disposal. This is an important issue, and I think that that's something that needs to be addressed. So just some closing remarks. I think we've made some tremendous progress in developing greener materials over the last 10 years in particular. I think that the environmental authorities do need to help us out by trying to harmonize the rules and to encourage incremental progress, as I commented earlier. And the oil industry, and that's all of us in the service sector and the OPCO sector, the oil industry must strive to anticipate and exceed the standards that may be set in future legislation. Going back to the beginning of my talk, I think the oil industry needs better PR. We need a full-scale charm offensive and public education initiative to balance the disinformation that's put around by certain interest groups and NGOs. I think we can do that, and I think we need to do that. The E&P companies do need to support environmentally responsible technologies, not just at the corporate level, but at the field level too. No point just having lip service here. This is the real world. And the cost of waste disposal and treatment in the long term will far exceed the development costs of biofriendly materials that can be safely discharged. That's all, folks, and I thank you very much for your attention. I'm going to finish not with this wonderful environmental slide of a whale, but of a beautiful beach in Thailand, and hopefully we can keep the environment looking like this. Thank you very much.